This is our presentation on thermal remediation methods for ENVSE 408. In this video presentation, we'll cover the introduction, physical mechanisms, influencing factors, field implementation, demonstration level, applicability and limitations, and cost and availability.
Contaminated soils are a great threat to our environment today. Many toxic spills can seep into the ground and cause toxicity of the soils for many years after the initial incident. These contaminants can then leak into the water table and pose health risks for human and wildlife alike. One very successful way to clean up these spills is to use a method called thermal remediation. There are several ways to perform thermal remediation, but before we get into depth, let's take a look at what thermal remediation actually is. This method uses only heat in one form or another to turn contaminants from a solid or liquid form into a vapor state. This then allows for much easier extraction than if it were to be removed via physical digging. When in a vaporous state, the contaminants will move freely through the soil. The vapors are then collected using vacuums that are located at the surface. After collection is done, these contaminants are usually transported to a treatment facility where they are processed and disposed of properly. This can be done on site or can be off site depending on the site's characteristics. Now that we know a little bit about the process of thermal remediation, you have to ask yourself, why would I choose this process over another form of soil remediation? The answer to that is that the process is extremely effective when removing contaminants from the soil. It has been shown in the past to be almost 100% effective at removing these contaminants. The process usually lasts anywhere from 3 to 6 months. In addition to this, thermal remediation is very versatile. It has been proven to be a successful form of remediation for many different contaminants such as gasoline, chlorinated solvents, dioxins, and even mercury. This means chances are whatever you're trying to remove, thermal remediation will be successful. This is due to the wide range of temperatures that can be achieved through this method. Another aspect that shows us just how versatile thermal remediation really is the fact that it works in almost any subsurface type. Some examples of this are gravel, sand, clay, and even all the way up to solid rocks such as granite. It is also effective at any depth. Given that there are little to no limitations, thermal remediation is one of the best methods of soil cleaning that exists today. Here, we can see what a cutaway view of a thermal remediation setup looks like. In red, you can see the thermal heating elements delivering the heat directly into the soil. The thin, long gray lines with dots are typically some type of monitoring equipment that ensures that the heat levels remain consistent throughout the process. In the soil, you can see the contaminants dispersed throughout. This next video will help us understand the process of thermal remediation.
Contaminated soils are a threat to health and environment by polluting underground water, suspending future development plans on site, and often leaving the owner with significant liabilities. For instance, here in Kristianstad, Sweden, where a former dry cleaner caused a significant contamination with chlorinated solvents in the soil close to the drinking water resources. And is here in Stockholm, where the site had to be remediated before building of new apartments. Many in situ technologies have been used with modest success in reaching cleanup standards. This can be due to diffusion limitations, lack of contact between reactant and contaminant, etc. To overcome these constraints, Veolia offers subsurface heating technologies such as electrical thermal conductive heating. Electrical heater wells are installed in the contaminated subsurface. Only heat is applied to the subsurface using renewable energy. The heat spreads by thermal conduction below and above water table and is almost uniform for the entire range of soils. The technology works in geologies ranging from gravel, sand, clay, all the way to solid rock like granite to any depths. Thermal conductive heating technology is the only in-situ heating technology that can reach temperatures at several hundred degrees Celsius and can thereby treat any kind of organic contaminants with low to high boiling points like gasoline, chlorinated solvents, all the way to PCB, dioxins and even mercury. Contaminants are vaporized according to their boiling point temperature and extracted to the surface, vacuumed and treated in an above-ground treatment process. The heating process typically lasts 3 to 6 months, depending on contaminant type and concentrations. At the end, almost 100% of the contaminants are removed by electrical thermal conductive heating technology. The treatment of extracted contaminants in above-ground process depends on contaminants type, contaminants mass, etc. Contaminants could be captured by activated carbon, destroyed in a thermal oxidizer, or using other appropriate technologies. On sites with a high groundwater flow, we use steam injection because it can deliver significantly more energy than any other heating technologies and thereby overcome the energy removal caused by the moving groundwater. Using steam injection, we can treat volatile organic compounds and some semi-volatile organic compounds. In some cases, with special hydrogeological settings, the combination of the two technologies can be applied, which provides the most robust subsurface heating approach on the market today. Veolia in-situ thermal remediation technologies are robust, proven, mobile, and can be monitored from anywhere.
Thermal remediation can be done in 3 main ways shown here. Steam-enhanced extraction is the use of steam as a thermal delivery mechanism. This is very useful for areas with high groundwater flow. The next is electrical resistance heating, which is the example shown in the previous video. And the last is radio frequency heating, which utilizes radio waves to heat up the contaminants. Let's dive deeper into each one of these methods.
Next, I'm going to discuss the critical physical mechanisms by which the 3 thermal remediation methods work. This method of thermal remediation is steam-enhanced extraction. Steam-enhanced extraction is a thermal treatment method for DNAPL remediation using steam injection and extraction through a well. This process first starts with an injection of steam into the subsurface. The steam will give off latent heat of vaporization to the soil and groundwater. Condensation occurs when the steam changes to liquid water or from its gaseous form due to loss of heat to the surrounding soil and groundwater. Steam injection is done continuously to cause the soil and groundwater near the injection well to reach steam temperature for removal. The injection process continuously affects the surrounding soil and groundwater. It creates a moving variable temperature of water and steam. When it reaches the contaminated DNAPL, it will slowly start to move and reduce the DNAPL's viscosity. From this, the increased temperature will cause the absorbed DNAPL in the soil to potentially vaporize into a gaseous phase. This will cause the DNAPL to move towards the front or the recovery columns. The DNAPL gaseous phase may potentially turn into a DNAPL aqueous phase. This DNAPL phase occurs due to the surrounding temperature change of the soil and groundwater. The process will continuously occur until it reaches the extraction well, and then from here it will be removed successfully. This slide shows a basic illustration for the process of steam-enhanced extraction. There you can see on the far left there's a steam injection well, and then after there's a temperature change, the contamination mass in the middle will move or flow to the far right where you can see the recovery rail column. And then from there, it will be transported up to reach the water treatment center. The method is electrical resistance heating. Electrical resistance heating is a method that uses the flow of alternating currents of electricity to heat the soil and groundwater from the evaporation of contaminants. This process basically consists of electrodes that are installed in the well throughout the contaminated soil and groundwater. The electrode array is connected to a delivery power system that uses a standard, readily available three-phase power. This process begins by passing current between electrodes, causing the soil temperature to rise. This increased temperature results in the volatilization of contaminated compounds into the vapor phase, so they can be removed through vapor extraction techniques. This heats the subsurface to temperatures that promote evaporation, increasing the subsurface temperatures beyond the point that most VOCs and NAPLs are used to. Yet they are applied at low and moderate temperatures. This is a helpful procedure because it can boil water in all soil types. From the heating, that can increase the biological degradation and the chemical reactions. Then the evaporated contaminants are captured by the subsurface vapor system and conveyed to the surface with recovered air and steam. The combination of contaminants and the air/stream are then treated and separated. For electrical resistance heating showcases how the electrodes are placed into the ground vertically. And then from there you can see it is a fairly easy setup to follow. They could reach various depths, and the red portion on the illustration showcases how the main system is broken up into a vertical and horizontal heating zone. And then from here, the recovery zone is on top because the contaminated fluids are forced to the top for treatment. The process is radio frequency heating. Radio frequency heating is a process when radio frequencies alternate in an electric field, thus creating radiation heat. The two main mechanisms are the electromagnetic radiation and the applied electromagnetic field. Radio frequency heating depends on the electromagnetic radiation and not so much upon the heat conduction and fluid convection properties. This is due to the fact that radio frequency heating heats materials quickly and efficiently because of all the heat transfer occurs at a molecular level instead. The applied electromagnetic field interacts directly with the permanent and/or induced electric dipoles, and the dipoles are just an unbalanced charge, which happens to be present in the materials. Dielectric heating is similar to a microwave oven, although the microwave ovens heat on a smaller volume scale. The diagram provided displays how the two electrode plates interact. I couldn't find a very specific illustration, so I'm just going to talk about it a little bit. So the system is set up by employing borehole antenna radiators, and then these radiators provide control to the soil temperatures, and they focus on the subsurface heating patterns. The radio frequency heating systems can control the soil temperatures in a very wide range. This range varies from a few degrees to almost 200 degrees Celsius.
In this section, we'll be talking about the influencing factors for thermal remediation methods, including steam-enhanced extraction, electrical resistance heating, and radio frequency heating. Steam-enhanced extraction is used to treat the following contaminants: non-aqueous phase liquid, volatile organic compounds, trichloroethylene, tetrachloroethylene, non-aqueous phase liquid, chlorinated solvents, fossil fuels, and heavy hydrocarbons. Some influencing factors for steam-enhanced extraction include the contaminant to be removed and amount of it, the size and depth of the site, whereas the large and deep sites are ideal, level of groundwater flow, and large amounts of groundwater improve extraction. The soil type, whereas coarse soils have greater removal results compared to fine sediments, and uneven permeability levels can limit the removal rate. Homogeneity of soil can limit the effectiveness too, and geologic stratigraphy is important as well. Some of the contaminants treated using electrical resistance heating include volatile organic compounds, chlorinated volatile organic compounds, non-aqueous phase liquid, semi-volatile organic compounds, and petroleum compounds. Some influencing factors for electrical resistant heating include the contaminant to be removed and amount of it, the size and depth of the site, whereas large size and depth are not ideal due to energy needs, The soil type, where fine-grained soils are more electrically conductive, can be more efficiently heated. Unsaturated soil enhances the removal, and low permeability is better for less heat loss, but overall the method is possible in any permeability. Homogeneity can vary widely, and the salinity can limit effectiveness of heat generation. The soil temperature is also important, and due to the presence of a water system, it is limited to temperatures below 100 degrees Celsius. Radiofrequency heating is used to treat the following contaminants: volatile organic compounds, benzene, toluene, hydrocarbons, and polychlorinated biofuels. Some influencing factors for radiofrequency heating include the contaminant to be removed and amount of it, the size and depth of the site, which can greatly affect the cost and removal rate, and the soil type, which is not reliant on soil permeability, but conductivity is needed to absorb the RF energy, and soil temperature, which has been found at high temperatures to increase the removal rate.
Field implementation. The first one we have here is steam enhanced extraction, or SEE. Steam is used for the subsurface heating and typically is generated on site through combustion of fuel or gas. This combustion would be in a packaged portable boiler system. Non-condensable gases recovered during remedial system operations can be used as a supplemental fuel. Injection wells are constructed with equipment to control and monitor the pressure and flow of steam injected into the subsurface. At active industrial facilities, SEE is applied using excess generation capacity of pre-existing stationary boilers.
Ecologia can use steam injection technology to remove viscous, immobile contaminants, such as tar, from below ground. A steam boiler is the heart of this technology. This can be powered by electricity, gas, or diesel, depending on the scale and location of the project. Liquid and vapors can be removed by vacuum. The pipework must be heat resistant. Steam is injected into the ground via specially designed steel pipework. This is lagged and insulated above ground to protect the operators from burns. The extracted liquid and vapor are cooled. Some of the vapor will condense to a liquid at this stage. Then we remove any liquid from the extracted vapor. Naturally, we want to protect the air that we breathe as well as the ground beneath our feet. So the extracted vapors are cleaned before discharge by passing through a granular activated carbon filter. This also prevents any explosive vapors reaching the vacuum blower. A single vacuum blower can provide suction to 1, 10, or even 50 extraction wells. Insoluble oils or solvents are separated from the groundwater. The oil can often be recovered and reprocessed, which adds to the sustainability of the technology. The groundwater is finally cleaned using a granular activated carbon filter to remove organic contaminants. Specialized filters can also be used to remove heavy metals and other contaminants. The groundwater is now tested to demonstrate that it meets appropriate standards before discharge to the sewer.
The second one we have is electrical resistance heating, or ERH. Electrodes are typically consisted of graphite, steel, or electrically conductive material within a borehole. Arrays of electrodes are installed in the Target Treatment Zone, or TTZ. ERH uses an electrode system to pass electrical current through the thin layer of moisture that coats the soil grains. The electrode system uses current flow to create heat while the soil acts as an electrical resistor. Multiple stacked electrodes can be constructed in a single boring. Maximum temperature that can be reached corresponds to the boiling point of the water in the local region. This allows differentiation in the vertical or thick heating of the target treatment zone. Electrical power is delivered to the electron array by power controllers. Isolation transformers are used to ensure that the current applied in situ flows only between installed electrodes.
This animation shows how electrical resistive heating, or ERH, technology can remediate contaminated soil in a short time frame. The red mass represents TCE, an industrial solvent, in soil from several chemical spills. The black vertical lines represent conductive electrodes for the ERH system, installed 35 feet below ground surface. On September 9th, the ERH system is turned on, and electricity is passed through the electrodes. Due to the fact that soil is an excellent insulator, the electric current is converted to heat energy in the soil. As the temperature increases, the TCE begins to vaporize. The TCE vapors are collected by horizontal wells installed near the ground surface. These vapors are then captured and later destroyed using carbon filtration. In about 6 months, over 98% of the TCE was removed from the subsurface, and all of the remediation goals were met. For more information, please contact Jim Deppa or visit the St. John Mittelhauser & Associates website at the contacts shown.
The third one we have is radio frequency heating, or RF. RF heating technology imparts heat to non-conducting materials through the application of carefully controlled RF transmissions. The technology is applied by inserting a flexible coaxial transmission line and applicator, which is the antenna, system into one or more vertical or horizontal boreholes in the area to be treated. RF generators supply energy through coaxial lines to a multiple of electromagnetically coupled downhole antennae, and the subsurface material between the antennae rises in temperature as it absorbs electromagnetic energy radiating from the antennae. The antennae can be placed in boreholes that are dry, wet, or filled with other materials depending on the application. The antennae do not require electrical contact with the formation. The dielectric heating produced by the RF antennae extends elliptically away from the antennae and into the target formation. The radial extent of the heating pattern will vary as much as a function of the operating frequency, the length of the RF antennae, and the electrical conductivity and dielectric constant of the target formation.
This next section is the demonstration level section, and it describes some case studies where the thermal remediation method has been used. So for case study 1 is the steam enhanced extraction. This site was a former naval air station contaminated with chlorinated solvents and oil products caused by a leakage from a waste oil tank buried on the site. Steam was injected in 2 different intervals in 6 injection wells located outside the NAPL zone as shown in Figure 1. From the central extraction well, groundwater, soil vapor, steam, and volatilized contaminants were extracted. Boiling temperatures were reached at all locations and more than 2,000 pounds of contamination was removed. Soil and groundwater sampling was conducted in the area, and indicated more than 99% mass reduction within the target treatment zone. For case study 2, this was an example of an electrical resistance heating. Feasibility studies were conducted at this site to evaluate remedial technologies. Multiple investigations conducted with more than 1,000 groundwater samples and more than 300 soil samples taken. In conclusion, electrical resistance heating was the best technology to treat the DNAPL source area. This process would require electricity flowing between subsurface electrodes and heating the subsurface. Steam is produced in situ and heats the tight soil lenses and DNAPL hotspots. Finally, mass is extracted in vapor phase and treated by steam regeneration carbon. A minimum of 47,105 pounds of mass recovered or destroyed in situ via hydrolysis. The average daily mass removal rate was 113 pounds per day. For case study 3, this is an example of radio frequency heating. This site took place at Mount Washington, Massachusetts. A release of 1,1,1-trichloroethane occurred at an active manufacturing facility. Residual TCA-dense non-aqueous phase liquid, or DNAPL, contamination was identified in an approximate 232 square meter source area at concentrations between 410 to 100,000 milligrams per liter. After evaluating several in situ treatment technologies, an integrated radio frequency heating and soil vapor extraction system was designed, constructed, and began operation in December 2003. The treatment system included a network of 9 100-foot deep, 8-inch diameter boreholes, an RF generator, a 4-probe transmitter array, and a SVE system for control and treatment of vapors. The RF heating system consisted of a 27 megahertz, 4-channel, 20 kilowatt RF equipment trailer, transmission lines, 4 watertight antennas, applicators, and fiber optic thermometry. The RF heating system operated for 36 months at a maximum output of 19 kilowatts. In conclusion, TCA concentrations in source area groundwater were reduced by 97%. The advantages of this technology was that RF heating preferentially heats polar molecules such as water, focusing the thermal energy on the target, impact groundwater and bedrock fractures rather than the host or the bedrock. Second advantage is that RF heating efficiency was enhanced by several site hydraulic characteristics, which included the low yield of the bedrock, the overlying building acting as a cap in minimizing infiltration of precipitation, and third, the hydraulic location of the site at the upper edge of a drainage basin divide.
So this section of our project is going to focus on the applicability and limitations of thermal remediation methods. So here's an overview of thermal remediation applicability. In situ thermal treatment is applicable for sites with significant contaminant mass. Effective fluid extraction is crucial during the thermal treatment process. This is done by maintaining both hydraulic and pneumatic capture within the treatment zone. Soil vapor extraction is the most common for fluid recovery. Once the recovered fluid reaches the surface, traditional methods such as sedimentation, filtration, and adsorption processes that use granular activating carbon columns may be used. Carbon for the adsorption process can be regenerated on site with steam. Being able to regenerate your own carbon packing material on site will save many costs in terms of waste disposal. Thermal remediation also excels in sites where the fractured rock is below the water table. This includes sites where the fracture porosities, or the fracture pores, may even be smaller than the soil porosity. And one of the more powerful things about thermal remediation is that it officially works in tandem with other in situ treatment methods, such as bioremediation. So during the thermal heating process, the bacteria from bioremediation will actually begin to grow faster and absorb more of the contaminants. So the figure I included on this slide is a specific thermal remediation treatment method called steam enhanced extraction. It shows you that you can actually use this technology to remediate directly beneath buildings. Thermal remediation can be applicable in typical and non-typical sites. It works effectively beneath industrial, commercial, or inhabited residential buildings, and it minimizes the surface and subsurface disturbance. It can also treat below the water table, and some studies have shown that thermal remediation has been able to treat at depths beyond 100 feet, and traditionally has treated Dean apples in the saturated zone at these depths. It has also been able to treat in areas with low permeability. This could include things such as like bay muds or tight clays. It can also treat fractured, heterogeneous rock formations. So as you can kind of see in the figure that's attached here, we're looking at sequence type 7 or sequence type 8. One of the limitations is that you have to ensure that existing monitoring wells and, previous borings are closed within your treatment area prior to the actual heating remediation. Open or closed wells can create a significant increase in pressure and temperature. Another limitation of this treatment method is that the existing buried utilities must be identified. This causes the design of the thermal remediation system to be dictated by these features. It's important to identify and control utility corridors where sewer or networked piping may exist to ensure that these features do not act as pathways for contaminated vapor to migrate into buildings or into the atmosphere untreated. Another limitation with this treatment method is that the number of existing vendors is limited, and even furthermore, in situ thermal treatment technologies are growing but are being subject to patent protections and licensing requirements. As of 2015, there's actually only 6 commercially licensed vendors to complete these projects. Another limitation of thermal remediation as a whole is that these systems can generate a significant amount of hazardous fines in the wells. This can be avoided though through proper well management and using things like well screens and sandpacking. So steam enhanced extraction applications. So one of the most powerful applications of the steam enhanced extraction is that steam is generated on site through combustion of fuel or gas. But on active sites where steam is generated in the manufacturing process in their facility, through boilers or whatever, some excess steam can be used in the treatment process as well. And often this treatment method is used in conjunction with other remediation technologies such as ERH. In cases like this, steam-enhanced extraction is applied to the highly permeable portions of the formation, and ERH is applied to the less permeable areas. So this figure actually shows one of the many applications for steam-enhanced extraction. In this case, the treatment system is being applied in the basement of a active dry cleaning facility. And that's one of the many benefits of steam-enhanced extraction, is that it's relatively low disturbance. So you can have these pipes and these extraction wells and still manage to remove contaminants effectively. So now onto some of the limitations of steam-enhanced extraction. The first one just comes down to thermodynamics, where water actually has a 4.5 times greater heating capacity compared to air. One of the other limitations is that steam-enhanced extraction struggles with low soil permeability, which often leads to low steam injection rates. Ultimately, this increases the heat loss to the overburdened and underburdened soils. Additionally, the vapors can condense around the unheated wells that are not being used for the thermal remediation quite yet, and these vapors can actually mobilize away from the site area. The idea of this treatment method is to work from the outside of the plume and then work your way in. These sites may require an impermeable surface to limit the infiltration from either groundwater or rainwater, depending on what kind of climate you're in. Lastly, the system associated with steam-enhanced extraction and the high temperatures that are associated with the steam may be unsuitable for some of the materials that are traditionally used for wells. Grout, PVC, and things of that nature may not withstand the corrosion and temperature of the steam. The next specific thermal remediation method we're going to talk about and its applications are electrical resistance heating. So typically this is used at sites that are characterized by heterogeneous and low permeability lithology. It's often chosen for low permeability sites because these sites usually limit the use of fluid delivery based remediation techniques. It can also be used to heat discretely, both horizontally and vertically, through bed fractures. This treatment method also excels with sites that have both coarse and fine grain, as well as interbedded fine and coarse grain strata, as well as fractured bedrock. This is typically in sedimentary rock formations such as sandstone and limestone. So some of the limitations with electrical resistance heating includes sites with high groundwater flow, typically around 1 foot per day. So this deals with the fact that it's good with sites with low permeability. So generally those sites do not have high groundwater flow, and highly permeable sites will have high groundwater flow. And with the case of high groundwater flow, it'll actually act as a continuous heat sink where the required subsurface temperature needed for treatment cannot easily be reached. To still implement electrical resistance heating in conditions like this, a groundwater diversion may need to be created, such as grouting. Electrical resistance heating also struggles at sites that have low media conductivity, typically caused by debris. So this could be at things such as landfills or just abandoned waste disposal sites where the soils are no longer untouched. Last limitation for this method is that water actually needs to be added around the electrodes. This is to prevent soil drying and just to ensure that electrical current maintains consistent throughout the treatment process. So the last specific thermal remediation method that we're going to talk about today with its applications is radio frequency heating. Radio frequency heating is usually used on sites where steam-enhanced extraction is ineffective due to the geological conditions, such as low permeability of the subsurface. If you were to model the temperature profile around the contaminant for this remediation method, you would see that it's often more uniform and reaches higher heating rates than the other thermal treatment methods we talked about before. This is because radio frequency heating, it's just one of its characteristics is that it's independent from soil geology and composition, unlike electrical resistance heating or steam-enhanced extraction. No extra fluids need to be injected for this thermal remediation method, so this ultimately minimizes the risk for contaminant mobilization or transport out of the targeted treatment area. Just like some of the other treatment methods we mentioned before, it has a higher flexibility and has the capability to be operated in logistically harder site locations, such as beneath buildings. And since radio frequency heating is independent from soil geology, you don't need quite the understanding of the hydrogeological conditions compared to the other remediation technologies. So the main limitation for radio frequency heating is that there's a limited number of vendors and contractors that specialize in this specific technique. Generally, this method is used in the oil industry for oil extraction of dense and viscous oils such as oil sand and shale. The second major limitation of radio frequency heating is that the generators, transmission cables, and antennas have to be custom made in certain applications. This is generally associated with very high capital expenses. Another limitation of the radio frequency heating thermal treatment method is that the transformation of the power line frequency in the transmission cables is typically 50 to 60 hertz, and that transition from the power line frequencies into radio waves often leads to an energy loss of 40 to 50% when compared to a system like electrical resistance heating.
Okay, so the next section that we have is the cost and availability section. So for cost information, there are two key cost drivers. The first is soil type, and the second is thickness of the contaminated area. The soil type affects the porosity of the soil and can cause more contaminants to be in the soil and harder to get out. And the thickness of the contaminated ratio, which is also called the depth to top ratio. If there's a larger area, there's more contaminants that need to be taken out of the soil. Also, the contaminants make a difference when cleaning up a contaminant spill. Some contaminants can be harder to get rid of than others, and all of these sections will be discussed later in the coming slides. So, soil type is the primary cost driver. It determines the soil permeability and porosity. So, for thermal treatment, soils of lower permeability are less expensive to remediate,
since they require less gas flow. So for example, silts and silty clays have lower permeability, so these are ideal for thermal methods of remediation. The following determine the need for pretreatment of soil before thermal desorption. So the clay content, the particle size, the moisture content, and the pH all affect the cost of the overall remediation of the soil. This is used to avoid such operational problems such as slagging and clogging of the feed mechanism while you're remediating the soil. And something to lower this cost and time that you're spending on it would be pre-treatment. And for things like this, pre-treatment may include things like screening to adjust particle size, chemical treatment to adjust pH, and dewatering to adjust the moisture content in the soil. So the next area of a cost driver is the contaminated area, which this is a secondary cost driver, which is the depth to the top and the thickness of the contaminated zone. So a deeper and thicker region of contaminated soils has higher remedial costs because it's a larger area and you're trying to get more contamination out of that area. The type of contaminant is a third cost dependent factor. There's a higher cost associated with contaminants such as like PCBs. There's also the concentration of the contaminant makes a huge difference in how you're remediating it and the cost that's associated with this. So the type of concentration of contaminants affects the operating temperature, the need to operate under a vacuum, and with a reducing or inert atmosphere, the type of off-gas treatment that's needed. So, for example, thermal desorption of soils that contain high concentrations of chlorinated compounds generally uses higher temperatures, is performed under a vacuum, and uses more complex off-gas treatment. So the overall cost analysis, as larger quantities are treated, unit costs are decreased, which we can also often see with any other thing in economics. If you're buying in bulk, your unit cost goes down. So, for example, when there's about 20,000 tons of soil that's being treated, the cost is around $100 to $300 per ton of contaminated soil treated. So, say the price is $300 per ton of soil being treated and you're treating 20,000 tons, the cost is about $6 million versus at $100 per ton and 20,000 tons, the cost is about $2 million. So this is about a $4 million difference in price. So you want to limit that as much as possible. So when the cost is decreased, whenever you're treating a larger quantity of soil, cost is decreased to $50 per ton and lower. So that is about a $1 million price count for if you treated 20,000 tons. Obviously, you would have to treat more to get that price point, but it just gives an idea of how much money you could actually save by treating a larger quantity of soil. There was no correlation that was found between cost and moisture content or treatment temperature, and those factors tend to be site-specific for treatment purposes. The next slide has a graph of like different situations and scenarios where you're treating. In the large sites, you are spending significantly less per 1,000 cubic yards, which once again is because you're treating a larger quantity of soil, so it gets the unit price down significantly. They left the media type, contaminant, approach, and just changed the soil type and permeability in Darcy's. So it gives you an idea of how the permeability really affects the price point, and the different type of soil has a different permeability than others. So that's a analysis on the different size and soil type. So the availability information, this remediation method is best for large contamination areas to remediate large quantities of soil. It is also the type and amount of maintenance needed for the thermal desorption system can affect the project schedule and cost. So if you're treating a larger quantity, once again, of soil, the cost goes down. And then depending on the type and extent of maintenance needs, the design and operation of the thermal desorption system may be modified, which it's, once again, that site-specific bit of information. And then the following slide is the references for this section, so you can look at those if you want more information on cost.